Hello, I am Hanaram. Welcome to alistenphysics.com. In this video, I will tell you about length shift. Length shift is an event that occurs between objects moving relative to each other. Here, I will tell you the details of how this happened. We see our environment with electromagnetic waves coming from our environment. Here, an observer sees his or her surroundings with electromagnetic waves coming from the sky and the city, reaching him or her. I said that the length shift is an event related to sight event. Here's an observer and a car. The car is standing here, while the observer sees the car in this way while it is standing still. If the car is moving away, she or he will see it shortened in this way. And if it is approaching, she or he will see it as elongated in this way. Now we're going to look in detail why this is so. How she or he sees it that way. Of course, the observer is looking at the car from behind or from the front. This is how we examine the case from the side. Therefore, we can think of how the observer sees it this way. The observer sees the car from behind, or the front like this, while the car is stationary. While the car moves away, she or he sees the car shortened. While the car is approaching, she or he sees the car getting longer. Moving on. Length shift is a very effective mechanism. It exists wherever there is movement without exception. And space, in particular, is a place of great distances and great velocities. Of course, the effect of length shift is palpably great here. Here is a nebula. We're taking a picture of the nebula here. But here we see the length shift version of this nebula, so we don't see its true form. Of course, we see a picture from years ago. Maybe 2 million. Maybe 3 million years ago in a similar way. But we are not talking about that either. In other words, a deformation occurs on the image. We see this picture with that deformation. Now when I go into details, you will understand better. Now since this is about seeing, let's examine a sight event. Let's take a look at the situation of seeing and before. Now, we have an observer here. There are various objects. These yellow points you see are the reference points. The task of these reference points in animation is to send an electromagnetic signal to the observer. They represent it. Normally, this task is done by the atoms that make up the object. Atoms send out electromagnetic waves, and the observer sees the object. But we will explain the situation using only such a limited number of reference points in animation. Now look, you see an arc like this. It's actually a circle. According to the observer, this is a circle centered on the observer and shrinking towards the observer with the speed of light. It comes towards the observer with the speed of light. And this circle, you see, while passing over that object, the yellow dots, the reference points, leave a signal to the circle. There, look, it left the signal in this way. And the number of electromagnetic waves on the circle is increasing as they come towards the observer. And a group, the signal group, is being formed. I call this formation the electromagnetic wave packet. And they arrive at the observer as a package. The observer sees these objects with the information in this package. Now, the crosses here are according to the observer's reference system. Here is an information that gives the coordinates of these yellow points. Define points according to the observer. Of course, each yellow point sends the information about the object and related to itself. And as a result, the observer interprets the incoming information and sees the objects. Now we need to think about one more thing before we move on to length shift. Source object and image object. These are separate concepts. Now, here I used a single reference point for the car. Look, there is a single yellow point like this. We do the same thing. At the moment, the car is standing here. Circle is coming left the signal. The signal arrived. The observer saw the image of the car at this point. So, what's happening while the car is moving away? Now, the car is moving away. Look, like this. Now, it left the signal. This is a point defined according to the observer's reference system. The signal is coming to the observer from that point. Arrived at the observer. The observer saw the image of the car at this point. So there are two concepts here. Real object, namely source object, and image object. We never see source objects. What we see are always image objects. If we ask the observer where is the car, she or he shows here, not here. Let's do it again while the car is approaching. Relative to the observer, the point the signal is coming from is here. So she or he will see image object here and saw image object. Source object. Now, let's see how the length shift occurs. Objects have width, length, height, are three-dimensional. Therefore, using a single point like this works in terms of finding the coordinate of the image object, as in the previous animation. Okay, but that doesn't show us how the length shift occurs. In order to show the length shift, I need to use more reference points for such a moving object. Here, I used such reference points surrounding the car. Now let's do it while the car is stationary. Then we'll see how it happens while the car is moving. Now, this is how our circle comes. The reference points here left their signal on the circle. The packet formed and arrived at the observer. The observer saw the image object in these bounds. So, let's see what's happening while the car is moving away. Circle is coming. Signals are left. Look, relative to the observer, the points where the signals are broadcast, the points where they set off, and the packet was formed, arrived at the observer. How will the observer see? She or he will see the image object between these points. As we can see, the image object is shortened in length because the source object is moving away. There is no change in the source object. Length shift does not occur on real objects. It is an impact that occurs only on image objects. Here we also do it when the car is approaching. Left the signals. The package is coming to the observer. Arrived. What happened? The image object will be located within these boundaries. Therefore, the observer saw the car is elongated. Of course, in the animation here, the speed of the car is half the speed of light. The car moving with the speed c2. That's why we see the effect of length shift so clearly. Of course, such a thing does not happen in our daily life. Because look, that passes with the speed of light. That circle comes with the speed of light. Now, the car has to be very fast, so that such a difference can occur. Right. Only at high speeds or very large distances does the length shift become obvious. Apart from that, of course, we do not have a chance to observe this effect in our daily life. Now that we have learned how the length shift occurs and its mechanism, we can now create its mathematics. I used a ruler here instead of a car for mathematics. Now, this is our arc. The animation starts when the circle is at point A. And at this point the ruler broadcasts a signal. Signal 1. When the circle moves, ruler moves in the direction of the arrow. When the circle reaches the other end of the ruler, a second signal is broadcast from here. Signal 2. Electromagnetic wave package is formed. When the package arrives at the observer sees the image object between points A and C. So where is the object itself? Here between the points D and E. What is the length of the ruler? D0. What is the length of the image object? It will be AC D1 distance, the length of the image object. What is D2? Within the time the signal came from point A to point C. The ruler came from point B to point C. So, this distance is the amount of distance two objects move away from each other during this time. Now, this gives us all the necessary information. From that, we get the mathematics. Here shortened length of the ruler is equal to the original length times this mathematical expression. Now, of course, a seeing eye immediately sees the existence of Alice's law here. Let me also point this out. So, receding objects appear to be shortened in length. Now, of course, length shift is still active while I am walking here, but of course it's not noticeable. The important thing is to be aware of the existence of this effect. So we're going to keep it in mind. You never know when it will appear. Let's do it while the objects are approaching. Now the ruler is moving in the direction of the arrow. Our circle is at point A. Let's start animation. Signal 1 broadcast. When the tip of the ruler reached point C, a signal was also broadcast from point C, signal 2. The package arrived at the observer. The observer saw the image object between points A and C. Meanwhile, the source object is between points D and E. Real object length. The length of the image object. The amount of objects getting close to each other. From that, we get again the mathematics. If objects moving relative to each other are approaching each other, the object appears to be elongated in the direction of motion. Here we got it. Of course. You might wonder at what speed this ruler would have to move for that much of a length shift to occur. Let me also show this. Now, look. The signal comes from point A to point L in t0 time. If we give the speed of ruler v value, the ruler drives AE distance in t0 time. This distance, right? So, if we divide the distance AO and distance AE like this, we find the speed of the ruler in terms of c. So, here, the speed of the ruler is 0.12 c. Now, we also learned the mathematics of length shift. Now, then we can move on to more serious, more striking issues. Look where we are coming from. Doppler effect and length shift. We got the math of length shift here, on the previous page. This is the Doppler shift equations. These are equations known in physics for 150 years. When we look at them, v values here show the same case. As the speed at which two objects move away from each other or approach each other. C is the speed of light. Here it means that by using these mathematical expressions, we can obtain these equations. It says here that if you know how much the wavelength changes in an observation, you can understand how much length shift has occurred. Or you can see how much the length shift occurs from the frequency as well. These are equations that immediately give the truth, of course, extremely important equations. So we have done with the Doppler shift. Now on this page I'm going to show you how the length shift relates to the math of C plus V C minus V. There are two animations on this page, above and below. You see both animations show the same thing. This object, this observer, initial positions are equal. Their velocities are also equal. But while the object is moving in one, the observer is moving in the other. If the object is approaching here, the observer is approaching here. Now let me talk a little bit about the Galilean relativity principle. Now this principle says, all the laws of physics are the same for all reference frames moving with a constant speed relative to each other. Alice's law also likes this Galileo principle very much. We can say Alice's law protects, depends on, entrusts herself to Galileo principle. If you want to prove that Alice's law is wrong, you prove that the Galilean relativity principle is wrong. At that time Alice's law becomes a cloud. Now, according to the Galilean relativity principle, the same image object will appear in both animations. The Galilean relativity principle says that. That principle says it doesn't matter who stops, who goes, the same event will happen. The observers will see the same image objects. So, do they see the same image objects? Let's prove that they see the same image objects. We proved. Now, look. The important point here is that the animation above is an animation prepared in the light of the information of classical mechanics and electromagnetic theory. It is incontestable. Because look here, the signals come with a speed of c, both according to the blue-clothed man and to the observer. Look like that. These are coming with the speed c according to that. We put and take out the image object. Now, in the animation below, in order to achieve the same result, the speed of the signals here must be c minus v relative to the blue-clothed man, that is, relative to the ground reference system, so that the same image object can be obtained. So, there is only one mathematical solution here. This means that if you want to get the same image object, you have to set signal speeds to c minus v. There is not another mathematical solution, so here, we have done the proof of c plus v c minus v math in this way. This is a proof in the geometric way. Let's do it while the objects are moving away from each other and close the subject. Starting. Image objects. How did I set the signal speeds here? I ran it with c plus v according to the ground reference system and got the same image object as a result. Let's prove. We proved in this way. There is something that is overlooked here. So what is the speed of the signals relative to source object? To source object, relative to the source object broadcasting the signal. I also talked about it in old videos. This is an outgoing signal. Since it is an outgoing signal, relative to the source object broadcasting the signal, the speed of the signal sent to a moving object will never be c. What will be happened? Here it will be c plus v. The velocity of these signals with respect to the source object over there is c plus v, with respect to the observer c. Of course, as you study Alice's law, you have the chance to better understand what it is I am passing. Could the theory of relativity have an effect on length shift? Now I have to mention this issue. Alice's law has actually ended the relativity theory. I have explained how this happens many times before. Here too. I will show you how to seize the existence of special relativity in relation to length shift. Now, this is the object and this is the observer. Object is moving away. As you know, we were able to obtain the image view of the object from the way we know. But as you know, the theory of relativity predicts that the real object, namely the source object, will shorten in length in the direction of motion. So let's add that effect here first. We accept from the beginning that the object has shortened in the direction of motion. And we run it and get the image object. Now, this image object is a figure obtained with both relativity theory and length shift of Alice law. Let's take a photograph of this figure. We got it in this way. So, if we ask the theory of relativity, how will you get the image object? It will tell us about it, won't it? There is no different thing here. Alice's law has already shown you how the image object was obtained and its logic. Here all we do is add the length contraction case to the object. Okay, now let the observer move away. Object was moving away not long ago. Now let the observer move away. We do the same thing again. Now, in order to achieve equality between image objects, I must first accept that the object will shorten in length in this case, so that I can achieve equality between the images. In other way, these images will not be equal. We say that according to the Galilean principle, let's make a logic that even if this object does not move, it will shorten in length, because it is moving relative to this object. Let's use again the impact of special relativity here. We have made the object smaller in the direction of motion. Additionally, we complete the motion and get the image object. Are these equal? Yes, these are, but now, the special theory of relativity has to choose the velocity of these signals as c plus v relative to the object, or ground, in order to achieve equality in this case. Otherwise, it won't be able to get this image object. Now, if it accepts the c plus v case here, if the speed of the signals says c plus v, then the question is, why did you write the special theory of relativity? Therefore, it is not possible for special relativity theory to accept this situation here. Therefore, it is impossible to obtain an image object. There is only one alternative. If it does not execute the signals with c plus v, here, it cannot achieve equality between image objects. Therefore, the image object cannot be obtained here together with the special theory of relativity and length shift. Therefore, cannot provide equality between image objects. Now, it must throw the towel in this situation. Because to accept this situation means to do harakiri. In fact, Alice's law leaves no other choice for itself. In this way, it is possible to terminate the special theory of relativity again by using length shift. Here I showed you this. Now I told you that the Galilean relativity principle is extremely important for Alice's law. There are two frames here moving relative to each other. This frame moves in the direction of the arrow. This frame moves in the direction of this arrow. Case in the frames is the same. While the object is in motion here, the observer is in motion there. Look, as a result, the same image object is obtained. But here, relative to this observer, neither is the speed of the signals here, nor is the speed of the signals there are c. Relative to the observer here, also the speed of signals over here is not c. Also, the speed of the signals there is not c relative to this observer. There is only one case where the speed of the signals is c. For an observer, the speed of the signals coming to him is c. In other words, such a mistake has been made in physics that everything has been turned upside down in the past. I wish you to save yourself from this big mistake as soon as possible. I am passing. There are some examples of length shift. Here are some examples such as what happens if the observer moves away, if the observer comes, if the object approaches, if the object moves away, if the object is like this, if the object is like this or that. Now the important thing is, you have seen the mathematics here, and also you have seen the logic of how to obtain the image object. The more reference points you create, the more detailed the image of the object will be. That's what I want to say here. After all, you can make these animations yourself. While Alice's law brings the mathematics of c plus v c minus v with itself, it introduces many new information into physics. You saw length shift here. You may be partially familiar with length shift, but I've shown here the relation between length shift and the math of c plus v c minus v. The mathematics of c plus v c minus v is extremely important for electromagnetic theory. Electromagnetic theory will use that mathematics in the future. Here you see, there are many subjects that I haven't told yet. This is all about the math of c plus v c minus v, for example. There is a Doppler shift, you see. How does Doppler shift occur? Why does it occur? Just as Alice's law explains the length shift here, it shows the Doppler shift in all its details, and I will make a video of it. I want to make videos of all these too, but apart from this I also have a lot of things to show. Alice's law is not a topic that will end. It is the future of physics. I know some of it. I haven't shown you everything about length shift here. For example, how it develops in accelerated movements. There are such interesting topics. Length shift is an interesting topic from the ground up anyway. It is an extremely important issue, as it relates to what we will see. For example, how does a length shift occur in rotational motion, right? So, there's a whole lot more to talk about length shift. It's not over. Although I have been working with Alice Law for many years, I am still learning about Alice Law. New subjects will also come up. Alice Law will not be limited to the subjects you see there. I suggest you move on to the math of C plus V C minus V as fast as you can. Good day to you all. I wish you good work.